thing and share my screen. Thank you, Zoe, for suggesting that we go through the extra reaction scheme questions that I created for you all, so we can start with that. And if anyone else has any questions, please feel free to message them through or unmute yourself and speak up at any moment. So again, this is not a formal lecture. We're not covering new material. So I would like to have this be a discussion as much as possible. So if you have any questions or thoughts that you want to share or ideas, that would definitely contribute to the discussion. So definitely please do so at any time. All right, so this first scheme here, we're starting with propane. And I don't know if I shared my screen. Yes, I did. Okay. So the propane is treated with excess Br2. So typically we would expect the secondary carbon to be more reactive because it can stabilize a free radical better than a primary carbon. So in the presence of light, that's the key thing there that helps us to recognize the bromine is going to split homolytically to produce a bromine radical, actually multiple bromine radicals. And then we do expect the secondary position to be much more reactive than the primary position. The primary free radical would not be effectively stabilized by hyperconjugation. So the bromine radical would abstract a hydrogen, leaving one electron behind there. And then that would likely collide with the Br2. It wouldn't be very likely to collide with the bromine radical because when bromine radicals are formed, the equilibrium in which they're formed favors the molecule since it has complete noble gas configurations. So it'd be more likely that the free radical on the carbon would bump into a molecule of bromine, which would produce another bromine radical and continue the reaction. So if it didn't say excess, I would assume that there's only one bromine for every one propane, and that this one product would likely be produced from that. But because I have excess, I expect that process to occur again. And through the same mechanism, I would likely end up with two bromines attached there. So that would be the expected substance to draw in this box here. I wouldn't expect the hydrogens at the primary sites to be reactive because the primary free radical that would have to go through as an intermediate would be a lot less stable than the secondary one. If I used excess chloride or bromide here, then I would expect the reaction to occur there. Because if you remember, we talked about that in chapter 11. We said the halogen bromine is selective for the most reactive carbon, but the chlorine and fluorine are really very unselective, especially fluorine, and they'll react with any hydrogen, even on primary carbons. All right, so now the next step is adding a strong base. And so the tert butoxide here, we expect to do an elimination. So on this structure, if I treat that with a tert butoxide, it needs to pick up a proton to balance its charge. And so if a proton is picked off to push out a bromine, that would make an alkene. And that would be where I would expect to stop if it didn't say excess. So if I have only 1 mole of this, for every 1 mole of this, chances are most of the molecules only undergo one E2 collision and produce an alkene, but if I have excess, I expect another terp-butoxide to get involved. I could imagine it picking off this proton, but when we talked about cumulated alkenes, we said forming two alkenes on the other side of the same carbon, it doesn't give the stability we see with conjugation. It's not as stable even as a triple bond. So what I expect here to occur, the most likely thing to occur would be the picking off of this proton to form a triple bond there to push out that Br. So that would produce this structure here. And there'd still be one hydrogen on there, which I could show if I wanted. So that would be the expected structure for compound 2. So now I've got to convert compound 2 into this compound here. So I need to determine what reagents are necessary. So here, if I draw in the hydrogens, just to make sure I can see what is happening, there's no change occurring over here on this primary methyl site. That's the same. But there is a hydrogen being added here, and obviously a bromine being added to the end. This hydrogen here is still there, so that's not changing. So basically what's happening is I'm adding a hydrogen and a bromine across the pi bond. But I'm only converting the triple bond into a double, so I'm only adding across one pi bond. So I'm only adding that once. But then the question is this Markovnikov or anti-Markovnikov? And so I can see if there are two carbons sharing a pi bond, and I'm going to use HBr, if I don't add peroxide, I expect the hydrogen to go to the carbon that already had more hydrogens. But that's not what I want here. I want the hydrogen on the other carbon. So this is an anti-Markovnikov addition. I need the hydrogen to go to the carbon that didn't already have more hydrogens to begin with. And so that requires me to use HBr and peroxides. And the point of the peroxides is that will open up to form free radicals. The free radicals will react with HBr to form a bromine radical. The bromine radical will then react with the pi bond. And that will start the addition across the pi bond. So then once I have this reaction, this product here, adding magnesium metal, there's no charge shown here, so I assume the magnesium has 2 valence electrons. It needs to be neutral, and that it will very readily get rid of those electrons to make its noble gas configuration. I expect those electrons to get inserted here between the carbon and the bromine to make a Grignard reagent. So that reaction should give this now with an Mg Br there instead of just a Br. It's the carbon magnesium bond that makes the Grignard nucleophilic. Right, we said the carbon's a lot more electronegative than bromine. It carries a large partial negative. So it should readily use those electrons to attack something. So now I have to decide, what is it going to attack to make this product? So let me do some analysis over here. So I've got this Grignard, and I want to convert it into this alcohol. So I'm starting with a molecule that has 3 carbons, and I'm converting it into a molecule that has 5 carbons. So I've got to add 2 additional carbons, and I notice that the nucleophilic site, which is carbon 3, is going to end up directly connected to the carbon where there's an OH. If there were an extra carbon in between here, then I could think about the Grignard attacking an epoxide. But here, I want the Grignard to attack a carbonyl directly because the Grignard carbon is going to end up directly connected to the carbon that this OH is attached to. So I need a 2-carbon group for that Grignard to attack, And it's going to have a CO double bond there. So basically, ethanal is an aldehyde. This this carbon will use these electrons to attack here and push those electrons up. So the first thing that will happen is that attack. So this is carbons 4 and 5, and I'm getting 3 to connect to 4. I'm glad Natalie's feeling better. Thank God for that. So carbon 3 is connected to 4. Electrons get pushed up to the oxygen. 5 is connected to 4. So then in a second step, I need some H3O plus and water because this oxygen needs to pick up a proton to become an OH. And since this ethanal is flat, the nucleophile can attack it just as likely from the top as from the bottom, pushing the oxygen into a solid wedge half the time, dash wedge half the time, so I can use a zigzag here to indicate both of those things are occurring. And so that's why I have that here in the product. All right, so the next step is I want to convert this compound into this diene. So basically, I want to do an elimination here. I've got to make the OH into a better leaving group and then add a base to pick off this beta hydrogen so electrons will swing in there. So the first step there would be tosyl chloride and pyridine to turn that into an OTS leaving group. And then this beta proton here is not going to be picked off because that would create a diene that's not stabilized by conjugation. So I want a base to pick this proton off, and there's really only one proton available to create the conjugated diene, which is going to be significantly more stable than any other diene. So it really doesn't matter what base I pick, there's only one available beta proton to make the most stable diene that's forming during the transition state and as a product. So it'd be kinetically and thermodynamically favored to form the conjugated diene system. But since it's not very sterically hindered here, maybe I'll just go with the terbutoxide again. And that would pick off that proton, push those electrons in, and then once this becomes an OTS, it would push that out, and that would make the diene. If I use PCC on this compound, PCC is an oxidizing agent, so it should oxidize primary alcohols to aldehydes and secondary alcohols, which is what I have here, to ketones. So the thing that PCC is going to do is it's going to enable this hydrogen to be picked off. These electrons are going to be able to swing in here, which normally can't happen on an oxygen because an oxygen already has a noble gas configuration. But first, this lone pair is going to bond to a chromium from the PCC, and so that's going to be able to take a pair of electrons away when this hydrogen swings its pair of electrons in. So that will give you this. Ketone. Right, so it's not changing the carbon skeleton, it's just converting a CO single bond into a CO double bond by picking off this hydrogen and that hydrogen and putting a pair of electrons between those two atoms. So now I've got a diene and a dienophile. So if they're mixed together, I expect what would happen would be a Diels-Alder reaction. So I would recognize that the single bond here can rotate. Double bonds can't, but single bonds can. And if that single bond rotates and some fraction of the molecules exist in the S-cis conformation instead of the S trans, which is how this is shown, and that's the major conformation most of the molecules will exist in. That can line up with this structure here. Didn't really leave myself enough space there, so I'm just going to redraw that. So here's the alkene or dienophile. And through the Diels-Alder reaction, I expect this pair of electrons to swing out here, this will swing out here, and this will swing in here. Right, circular, I can go clockwise or counterclockwise. But I want to number these carbons because it's really easy to make mistakes here if I'm not careful to pay attention to which carbons are involved in the reaction. Right, so this diene has 1, 2, 3, 4, 5 carbons. And we'll go from there 6, 7, 8, 9, 10. So there are 10 carbons total in my structure for compound 8. And I really have to pay attention to where the pi electrons are, right? So in a cycloaddition, like a Diels-Alder reaction, it's only the pi electrons that are moving. And they're only going to be able to connect the atoms that are part of those pi systems. So only carbons 2 through 5 and 7 and 8 are going to be involved in that mechanism. And so 2 is going to bond to 7 and 5 is going to bond to 8. If it's a Diels-Alder, meaning it's a 4 plus 2 cycloaddition where I've got 4 pi electrons on one molecule and 2 on the other, I should always be making a new 6-membered ring. So I could show now carbons 2, 3, 4, and 5 connected to 7 and 8. And this pair of electrons shifts in there, so I do also still have a pi bond between 3 and 4. So that makes the new 6-membered ring. Carbon 2 has a methyl group, and carbon 7 has a methyl group, right? So there's still 1 connected to 2, and 6 connected to 7, and 8 is connected to this CO double bond system, carbonyl system. So there are some stereochemical issues here, and we want to think about that a little bit. Make sure we get the right wedges and dashes wherever possible. So I have to keep in mind both of these pi systems are flat. So this alkene and the diene are not going to approach one another in the same plane. One is going to sit down on top of the other. And since they're both flat, neither has a chiral center, there's no way to control which one comes down on top of the other. Right, so if you recall, what has to happen here is the p orbitals of this have to overlap with the p orbitals of this. So the bottom p orbitals of one have to overlap with the top p orbitals of the other. So if in this format, this one here, the alkene, would come down on top of the other one. And since the methyl group, that's carbon 6, and the carbonyl, that's carbon 9, are currently trans with respect to one another, they would have to end up on opposite sides spatially. So when that occurs, if they sit down from the top, it'll push this methyl group down. So in some of the molecules, the methyl group here will be pushed down. That's if the alkene comes down on top, it'll form a sigma bond pointing out at me due to this overlap, and that'll push the methyl group into an away position. If that occurs, this methyl group here might be pointing away, and the carbonyl would have to be pointing out at me. Right? So one thing I know for sure is that these two groups cannot be both solid or both dashed, because that would require me to have used the cis alkene. Right? So only if the two groups on the alkene start on the same side will they both end up with both solid or both dashed. So since that wasn't the case, one would be solid and the other would be dashed. I could have also formed this. Right? They're trans to begin with, so they end up trans. And then there'd still be two more products, because the alkene could have come from underneath. It could have overlapped its top orbitals with the bottom orbitals of those carbons. That would have required the alkene to come from underneath, and that would have pushed the methyl group up there. So this methyl group could have ended up in a solid position. And that could have also happened with the opposite spatial configuration for the groups on top. So there are really four possible isomers that I could draw. I would want to draw all four of them for compound 8. All right, so that's that one. Questions about that, feel free to give me a shout out. So then there was this other reaction scheme here. This one starts off right away with the Diels-Alder. All right, I've got my diene. It's already constrained to the S-cis configuration. It's ready to go for a Diels-Alder. And similar to cyclopentadiene, this would probably undergo Diels-Alder with itself in the bottle at room temperature. So if you wanted to get this compound, you'd probably have to break apart the dimer of it that would exist when it undergoes Diels-Alder with another identical molecule and isolate that. But if we could do that, it should quickly react with this dienophile with an electron withdrawing group in the same way we just saw. So what would happen here is I would want to redraw this 6-membered ring. Oops, I made a 5-membered ring. We've been doing that a lot lately. There, add an extra carbon. So I've got my pi bonds here and here. So if I numbered this one, 1, 2, 3, 4, 5, 6, and I numbered this one in the same way, I would have 1, 2, 3, 4, 5, 6. So then the dienophile could come in here. And the diene is symmetrical, so it doesn't matter which of these two carbons the ester group comes in on. But we would have a Diels-Alder reaction, so these electrons would swing out to form a bond here. This pair would swing in to make a pi bond between 2 and 3, and this pair here would swing out to make a new sigma bond there. So that would give me a compound that looks like this, with the new pi bond here. And this group would end up in an endo position because the pi system of the CO double bond would be able to form London forces with the pi system of the alkenes underneath here. So that would be the expected major product here, resulting from the first step of this process. So how do I convert this into this? Well, when I look at it, I can see the bicyclic part of it's not changing. What's changing is the ester is being converted to an alcohol. So I've got to push out this methoxy group as a leaving group, and if I'm careful enough to notice, a couple new hydrogens here that weren't on this carbon to begin with, I've got to add new hydrogens. And so the way to do that is with LAH, lithium aluminum hydride, in one step, and then in a second step, H3O plus and water. Those cannot be added together because the hydride will react directly with the proton source. But let's take a quick look at that mechanism to review it. So I'm not going to redraw this over and over again because I'm sloppy and it takes time. I'm just going to call this whole thing an R group. So that R group's not reactive toward these reagents. So it will remain the same after the reaction. So that R group is connected to the CO bond OMe. And of the lithium aluminum hydride, the aluminum has a negative formal charge here, quite unstable. So it will release some electrons to attack and push electrons up here. R group's still there. Now there's a hydrogen there, and now I have the OMe here. And this methoxy group is not a great leaving group, but compared to the negative on the aluminum, it's more stable to put the negative on an oxygen. And compared to this negatively charged oxygen, if these electrons were to swing in and push that out, I would have this negative charge. So what's the difference? Neither one is stabilized by resonance or significant excuse me, hyperconjugation. The main difference is solvation. So with a small methyl group, the solvent can better be able to come in here and attract to this negative versus over here where this R group and the methoxy are probably blocking the solvent out, so it can't attract so well. So this is a favored step to push out that leaving group because the negative can be better solvated. And when this oxygen, and also two products have more entropy than one, so when this oxygen swings its electrons in to reform that double bond, that's again a product favored or forward favored step. So you might want to indicate excess lithium aluminum hydride because once this aldehyde forms, it will continue to be reactive toward hydride in the same way. So another hydride would be delivered here to push electrons up again. And that's how I get two new hydrogens installed on that carbon. And then the proton source would be provided for that. So whether it be H3O plus or water, the oxygen would pick up a proton, and that would give me an OH. So that's how the LEH works. Then the next step here we talked about is a protecting group that we're adding. So again, I'm just going to call this whole thing R. So the R, that bicyclic system would be connected now to a primary alcohol. And what's going to happen here is the oxygen of that can form a nice strong bond with the silicon of the trimethyl silyl-chloride. So what that looks like is this. And normally a tertiary carbon, this is a silicon, but normally a tertiary carbon can't be attacked by SN2 because it's too crowded. But the silicon is a larger atom. So with the larger atom and these methyl groups sticking out, there's enough space there for a nucleophile to come in and attack and push out a leaving group. So that's what's going to happen here. And then that creates a positive here. So the pyridine, which is a weak base, will pick off this proton and balance out the charge on that oxygen. So compound 3 should be the same structure except now the oxygen is protected with a silyl group. The point of that is to protect that oxygen so it does not react with MCPBA. And the MCPBA, we know, will convert an alkene into an epoxide. So that's what occurs next here. If I have an epoxide and I want to open that up, I need a nucleophile. In this case, this carbon here needs another 3-carbon group to be added. So I need to install 3 new carbons. I want that pi bond to be there, and I want this carbon to be the one that connects to the bicyclic system. So that carbon is going to have to be bonded to magnesium. I could set that up as a Grignard reagent. So a lot of times students make mistakes here with the number of carbons. I want to count 1, 2, 3, 1, 2, 3. Right? There's no carbon here. This is showing a bond between carbon 1 and magnesium. So it's carbon 1 that will attack and open up the epoxide. And a negative on a carbon, even a large partial negative, is less stable than a negative on an oxygen. So that will readily attack, alleviate that ring strain of the epoxide, and form the negative on the oxygen. But then if I want that to be an OH, I would need some H3O plus and water in a second step to provide that proton there. And I don't have to worry about that affecting this because it's protected. Then the next step is TBAF, which is basically supplying a fluoride ion. And fluoride forms an even stronger attraction to silicon than oxygen does. So this will attack that silicon and push this out. The TBAF also has a proton that's usually available so that oxygen can pick up that proton. So even though there's no box here, what should be occurring in this spot would be an OH there. So this is basically deprotecting the oxygen, removing that group, so now this oxygen can react. And we still have this and this. So then when that is treated with this set of reagents, we know this set of reagents does anti-Markovnikov hydration across a pi bond. So we've got one pi bond right here, and there's a hydrogen here. And that's piece. Put this down. There's a hydrogen here and here. So anti-Markovnikov occurs because the boron hydrogen bond of the BH3 has a polarity where the hydrogen is slightly negative and the boron is slightly positive. And so that will attract the pi electrons to the boron, and they will be attracted to the boron from this carbon so that a partial positive will form here, and then this hydrogen will bring its electrons in there. Right, so we expect the new hydrogen to add to the side where there was fewer hydrogens rather than more. That's why it's anti-Markovnikov. The boron will add here, and then the second set of conditions will replace the boron with an OH. And so structure for compound 5 starting to get better at drawing these. It would have the same number of carbons, which is 1, 2, 3, but now there's an extra hydrogen bonded on 2 and an OH. 1, 2, 3 bonded on 3. So So then finally, to convert this structure into the final structure, what's happening here is I'm doing an oxidation at each OH. The primary alcohols are getting oxidized all the way up to carboxylic acids. The secondary alcohol is getting oxidized to ketone. So we said there's a couple different sets of reagents you could use there. You could use the bromic acid or the potassium permanganate. Either of those should be strong enough to fully oxidize those groups up to their highest level of oxidation, which is what we see in the product. All right, any questions about any of that? Please send me a message. I'm going to pause this for a moment. And the questions I came up with were mostly focused on the content you're going to have exams on this week, since no one really requested to review any older material. So I came up with a couple naming problems because I tend to put those on exams from time to time, and I want to make sure you're prepared. So you may ask to give a name for a structure, or I may give you a name and ask you to draw the structure. So let's take a look at this one first. We want to name it. So there's a lot going on here, but the first thing I see is an aromatic ring. I really have two of them, but this aromatic ring is connected to a bunch of stuff, including a carboxylic acid group. So when I have an aromatic ring connected to a carboxylic acid group, that means my parent can and probably should be named benzoic acid. Right, so the name benzoic acid accounts for the ring and the carboxylic acid groups. And when I do that, that means I have to start numbering carbon 1 here. The carbon of the ring that the carboxylic acid group is connected to has to be carbon 1 if I'm using this parent name. And if you recall, we talked about this. We said there's other parent names. So if you have an aldehyde here, it'd be benzaldehyde. If you had a methoxy group here, it'd be anisole. If you had an NH2 here, it'd be aniline. So if you're using a parent name that includes information about the group attached to the ring, that carbon of the ring has to be carbon 1, and then we would just number around in whatever direction gives the other substituents the lowest numbers. So that means I've got a substituent on 2 and a substituent on 4. What's the name of this group on 4? Well, this is just a fully drawn out nitro group. It's really just an NO2, and the name for that is nitro, and that's introduced in this aromatic section. So I've got a nitro on 4, on 2, what do I have here? I've got a 1, 2, 3 carbon chain that has a methyl on 2 and another ring also on 2. So that would be called a 2-methyl 2-phenyl propyl. And that has to all be in parentheses because these 2's are not referring to carbon 2 of the parent chain, they're referring to carbon 2 of the substituent group. So this is the substituent that's on carbon 2 of the parent. Right, so just to be reiterating here, this 2 refers to carbon 2 of the parent. These 2's refer to carbon 2 of the substituent. And that's why all of this has to be in parentheses, because everything in parentheses is naming this entire substituent that's on carbon 2 of the parent. So then I would place those in alphabetically. M comes before N, and so the full name would be 2 2-methyl, 2-phenyl, propyl, 4-nitro, benzoic acid. Usually students do better with questions where I give you the name. So I also created one of those and I made it challenging. So what makes these easier is you don't have to really decide what order to look at this in. You just have to go to the end and find the parent name first. So benzaldehyde would have an aromatic ring with an aldehyde, which is a CO double bond with a hydrogen. So if that's my parent name, just like in the last example, if the parent name includes a benzene ring and a substituent, then the carbon of the benzene ring that the substituent's directly attached to has to be carbon 1. And from there I can number around right or left, doesn't matter. So I'll look at where my substituents are. There's nothing on 2, because all these other numbers are not 2. Right, this 2 here is telling me information about something that's occurring within the substituent. That's why it's in parentheses. There is something on carbon 3. So I want to look to name or draw something that represents this name. So what's on carbon 3? A butenyl group. So bute means 4. So I have 1, 2, 3, 4. For the bute. But the ene implies there's an alkene here, and that's what this 2 is for. It's telling me which carbon of the side group the alkene is connected to. And so it's bridging carbons 2 and 3. And there's a bromine on 4. So on 4, I would put a Br. So what I just drew here is a 4-bromo 2-butenyl group on carbon 3 of the parent chain. So that takes care of that substituent. On carbon 4 of the parent chain, which would be this one here, it says there's a cyclopentyl. So I draw a cyclopentyl, a ring with 5 carbons. Pent means 5, cyclo means ring. There's no indication of any double bonds there. And on 5, it says there's a tertbutyl. So I'll draw a tertbutyl group on carbon 5. So I made a mistake with this name because there are no chiral centers. So this S would not be there. So that's my bad. So what does this Z mean? Well, the Z refers to the configuration at the alkene. So I just, by instinct, because most alkenes that have their large bulky groups on opposite sides of the pi bond are more stable due to having less sterics, I drew it that way because it's more stable that way. But the name tells me whether that's correct or not. And a Z means that the priority groups are on the same side of the pi bond. Right now, I have them on opposite sides, so I have to fix that. So I have to take carbon 4 and the bromine and put them on the same side as the other priority group, right? The hydrogens that are here are lower priority. Obviously, they have lower atomic numbers than carbons. And so the 2 priority groups have to be on the same side if it's a Z configuration. And so that is necessary to make the structure completely correct for that name. so there's a couple naming examples for you. Hopefully that's helpful. I also created some structures here because we recently talked about determining whether something's aromatic, anti-aromatic, or neither. And so I want to look at that analysis for each of these examples. So to determine if something's aromatic, we know that there has to be full conjugation all the way around the ring. And what that means is each carbon or each atom, doesn't have to be a carbon, each atom must be sp2 hybridized so that it has a p orbital that can overlap with the neighboring p orbital side by side, and it has to be flat enough that those p orbitals overlap, right? There can't be rotations that cause one p orbital to be in a different plane from another because they have to overlap side by side. And also to be aromatic, we need it to have an odd number of pairs of pi electrons. Or another way of saying that is 4n plus 2 total pi electrons, where n equals 0, 1, 2, up to other whole number integers. To be anti-aromatic, it also requires the same criteria A, but criteria B is the opposite. We need an even number of pairs of pi electrons. Which is for n total pi electrons, where n is a whole number integer. And neither would just be any situation where those combinations of criteria are not met together with one another. So let's see if we can figure out what these molecules are. So the first one here, when you have a lone pair on an atom, like take a look at this nitrogen, it's got 3 single bonds, including 2 from the ring, and a lone pair. Typically we expect that to be sp3, because the sp3 orbital is more compact than a p orbital and allows the electrons to stay closer to the nucleus. But if the neighboring atoms have p orbitals, like these do here and here, then this lone pair the nitrogen could hybridize sp2 and put the lone pair in a p orbital. So it's got options. It will do whatever makes it more stable. If putting the lone pair in a p orbital makes it aromatic, then it will do that. So what we have to do here is to look at every atom. Every carbon here is sp2 because it's part of a double bond. And the nitrogen could be sp2. That could fully conjugate the ring. It could be flat as long as it has the right number of pi electrons. So let's count them. 1 pair, 2, 3, 4, 5, 6. That's an even number of pairs. So if I include the nitrogen's lone pair, that's 7 pairs. And that is exactly what we need for it to be aromatic. An odd number of electron pairs. If this electron pair gets in a p orbital, the lone pair there, and all the other ones overlap, that'll be the 7th pair. It'll be an odd number of electron pairs around a fully conjugated ring. And so that would be aromatic. And that would be especially stable. Let's take a look at this one here. So here, every carbon is sp2. There's no way to avoid that because they're all part of pi bonds. And got 1, 2, 3, 4 pairs. There's no way to make an odd number of pairs. So if I have an even number of pairs in a fully conjugated system, that's anti-aromatic. So that's not going to be a stable situation. On the next structure, 1, 2, 3, 4, 5. I don't know why I'm counting. Every carbon here has full conjugation, or is sp2, and has a p orbital overlapping side by side. This one here is very similar to the nitrogen. It's got a lone pair, and the lone pair could be in an sp3 orbital to avoid full conjugation if that makes it more stable, or it could be in an or it could be in a p orbital to overlap side by side to make more conjugation if that makes it more stable. It will be more stable if it makes it aromatic. It will not be more stable if it makes it anti-aromatic. So that's why we have to count the number of pairs. We've got 1, 2, 3, 4, 5 pairs. So that is a situation where the lone pair will be much more stable in a p orbital, so it can overlap with the neighboring p orbitals and create full conjugation for the ring and create a total of 5 pairs in those p orbitals, which makes it aromatic and will make it a lot more stable. This structure here is definitely neither because it's not a ring. So if you don't have a ring, you don't have an aromatic ring. That's a pretty straightforward one. So these other 4 won't take long to analyze. Looking at this structure here, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons that are all sp2. This one's also sp2. It's an empty p orbital. There's no electrons there. That's what makes it a carbocation. So how many pairs do I have? 1 pair, 2, 3, 4, 5 pairs. That's an odd number of pairs. Odd number of pairs, fully conjugated ring, aromatic. So that's going to be a lot more stable as a carbocation than most of the other carbocations we've seen. We know carbocations are generally unstable. This one is going to be stabilized through resonance over every one of these carbons. And the fact that it creates an aromatic system specifically makes it a lot more stable than it would otherwise be. This one here is definitely neither. Because this carbon is sp3. Every atom has to be sp2 for it to be aromatic or anti-aromatic. Looking at the next structure, I've got to check to see if the ring's fully conjugated first, and that depends. This carbon here could be conjugated with the others if it were sp2 and the lone pair in a p orbital. But it might also be sp3 and keep the lone pair out of p orbital if that makes it more stable. So what I have to do, again, is to count the number of pi electrons. 1 pair, 2 pairs, 3, 4, 5. So this one would be aromatic, specifically because the 5th pair, that's the pair that you need to make an odd number of pairs, is in a p orbital on an sp2 hybridized carbon, overlapping with the other ones all the way around, creating an odd number of pairs total. So this last one, every carbon is sp2. It looks like we have full conjugation all the way around the ring. And we have 1, 2, 3, 4 pairs. So that's an even number of pairs. So normally if you have a fully conjugated ring with an even number of pairs of pi electrons, that would be anti-aromatic. But when we talked about this in lecture, we said it was neither. So the reason it's not anti-aromatic is because it's not flat. We said this structure takes on a kind of a tube shape so that the p orbitals here aren't overlapping side by side with the neighboring p orbitals. Breaking up that overlapping side by side p orbital makes it more stable because it avoids the otherwise anti-aromatic situation that would result by having an even number of electron pairs in p orbitals. All right, if you have any questions about those, please message me anytime about that. So go on to another topic. Everyone's favorite topic, NMR. I'm not hearing anyone disagreeing with that thought, so I'll just assume that that's true, and that is everyone's favorite topic. So I might ask you a question too. Oh, okay, Amy's disagreeing. Fair enough, Amy. It's not everyone's favorite. Everyone but Amy loves it. So I'd probably ask you to look at both proton and carbon. Maybe, maybe not. Definitely, you want to at least be prepared to predict signals for both types of NMR and as well as determine a structure from given NMR signals. So we'll look at an example of each of those. So here we've got a structure. In order to predict the proton signals, we would want to start by drawing in all the protons so we don't lose track of any of them. And obviously that's the number that are needed to complete the noble gas configurations for the carbons. So for the proton NMR, how many signals will we have? Well, we have to look for hydrogens that might be equivalent due to symmetry. So this one here is definitely unique. I'll call this one hydrogen A. I can really start with any of the hydrogens, but I'm just choosing to start here. It's the only hydrogen on a carbon that's adjacent to a carbon with a chlorine. So it's definitely unique. Just kind of go around clockwise here. So are these two hydrogens here unique or equivalent to the two hydrogens here? They look very similar. If my structure were this, didn't mean to do that, where I had something like this, then these two hydrogens and these two hydrogens would be equivalent. Or even if I had this. If I can draw a line of symmetry through here where the top is a reflection or rotational equivalency to the bottom, then these two hydrogens and these two hydrogens would be equivalent. But that's not really the case here because of this chlorine and this propyl group are not the same. That means the conditions or environment on top of the structure where these two hydrogens are located is a little bit different from those on the bottom of the structure. So we don't really have exact equivalence between these hydrogens on these two on this carbon and those two on the neighboring carbon. So I would call these hydrogens B and these hydrogens C. Since there's no chiral center anywhere, spatially one of these has a solid wedge and the other has a dash wedge. There's no difference between those two. So spatially, there's no difference between those two, and so they're equivalent. So I'll call these two B and these two C. This one's unique. I'll call it D. These two over here be E, F, and G. So I've got a number of signals here, and I want to be able to predict for all my proton signals the shift, or at least a range of where I'd expect that to occur in units of ppm, the splitting pattern, and the integration. So we've got A, B, C, D, E, F, and G. So for hydrogen A, where would I expect that to be? Well, if it's on an aromatic ring, I don't yet expect you to be able to predict where in that range it will be. We are going to talk about that eventually. But for now, if it's on an aromatic ring, you can be as broad as saying it should be anywhere between probably 6 and 9 ppm. The splitting pattern for this hydrogen. If it's on an aromatic ring, it could be split by hydrogen on a neighboring carbon, but there are none. And it could be split by hydrogens even one more carbon away from that, but there are none there as well. So you want to look out for that. Not just splitting with hydrogens on neighboring carbons, but 2 carbons away is possible in an aromatic ring. But even then, there's no hydrogens there. So we'd expect that to be a singlet. And it would integrate to 1 because there's 1 hydrogen of that type. Looking at hydrogen B and C are not equivalent. So that means they'll probably be splitting one another. But first we want to talk about shift. So being a CH2, I expect that to be around 1.2 ppm. But since it's 1 carbon away from a carbonyl, that's probably going to add about 1 ppm to that. So that's going to be around 2 to 3 ppm. And those 2 of type B would be split by C into a triplet. Alright, the cat's getting into too much trouble, so I had to get rid of him. He's in a timeout, so here we go. That would be a triplet. Those 2 would be split by C. So because there's 2 hydrogens of this type, and we have an N+1 rule, that's where we get a triplet from. And that would integrate to 2 because there's 2 hydrogens of that type. So we did say B and C are not equivalent, but they're very similar because they both are 1 carbon away from a CO double bond, and they're both CH2 groups. So I would expect their shifts to be very similar, and that might overlap. And so I might see, instead of 2 separate triplets, that each integrate to 2, I might see 1 multiplet that integrates to 4. Because they'd be splitting one another, and those triplets might overlap. It might be hard to tell that it's a pair of triplets. And it would definitely integrate to 4 because there are 4 total hydrogens. So that's something you'd want to look out for if you actually had an NMR to interpret. Hydrogen D is similar to A. So it would also be between 6 and 9 because it's on an aromatic ring, directly onto the ring. And that one would also be a singlet because there's nothing on the neighboring carbon or even 2 carbons away on the ring to split it. 1 hydrogen of that type. And then E, there's no carbons on that neighboring hydrogen to split it, but there are 2 on this carbon of type F. And those 2 would create a 2 plus 1, splitting E also into a triplet. The shift for E would be probably around 2 because typically a methylene or CH2 group comes around 1, but being 1 away from the aromatic ring would shift it down an extra unit. So that'd probably be around 2 ppm. That one integrates to 2. F would be a little bit tricky, so we'll come back to that. Let's do G first. G is a CH3, and it's got 2 neighboring hydrogens. So 2 plus 1 would also make that a triplet. A typical methyl group that's not close to any electronegative atoms or pi bonds or anything would come around 1. And that would have an integration of 3. So hydrogen F is trickier because it's being split by both E and G. E splits F and G splits F. There are 2 hydrogens of type E and 3 of type G. It's possible that all 5 of those would be splitting F with the same coupling constant. If that's true, I'd have a 5 plus 1. It would be a sextet for this splitting pattern. It's also possible, though, that the methyl group is splitting with a very different coupling constant from this CH2, or at methylene. If that's true, the CH2 would split it into a triplet, and the CH3 would split it into a quartet, or 3 plus 1. So I might see a sextet if they're all splitting with the same coupling constant. I might see a quartet of triplets, or a triplet of quartets. So there are really 3 possibilities there. But F would probably come around 1.2 ppm because it's a methylene and it's not next to anything that would de-shield it. It would represent 2 hydrogens, and the splitting pattern here would be either a sextet if all 5 hydrogens were splitting it with the same coupling constant, or it could be a triplet of quartets, or a quartet of triplets. So I might be looking for you to explain each of those different possibilities in your answer if you had a question like this on an exam. So, what about this over here then? You've got some NMR data, you want to try to draw a structure. So, what can we do? Well, we've got a lot of data here, we've got to start somewhere. So, what I might do to start is to look at the carbon NMR, because depending on where the signal shows up in the carbon NMR, that tells you about the hybridization of the carbon, whether it's bonded to something electronegative or not. And so I might just want to get that information out there. So between 150 and 150 and 220, a signal that appears in that range is usually part of a CO double bond. I can't really tell much more than that because I don't know where in that range that signal is. Signals between 100 and 150 are part of a carbon-carbon double bond or an aromatic ring of some sort. Signals between 50 and 100 for carbon are usually when carbon's bonded to something electronegative like oxygen. And signals between 0 and 50 are, these are both sp3, and that's a carbon that's just got 4 bonds to stuff. We don't really know what to. And so that gives me a sense for the types of carbons. I've got 2 carbons of this type. I've got 10 carbons of this type. So the more signals I have between 100 and 150, the more likely it is going to be some ring, or in this case, possibly fused rings. If I've got 10 of them, I can't just have one ring, because even if each carbon were different, like maybe I had some, substituents here that are different, so the ring's not symmetrical and each carbon of the ring is unique, that would still only give me a maximum of 6 signals, not 10. So maybe I'm looking at trying to fuse a couple rings together, because that would give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. That would give me 10 carbons as long as they're aromatic, fully conjugated all the way around, and as long as there was some asymmetry, right? This molecule right here has got symmetry. Because these 2 fused rings are equivalent, if there were nothing substituted on this system, then these outside carbons would all be equivalent. These carbons right here would all be equivalent, and these carbons right here would be equivalent. So I would only see 3 signals. So to get 10 signals, there's got to be some substituents here. One of those is going to have to involve a CO double bond. One's going to have to involve a highly electronegative atom with another carbon and a couple more carbons. So I've got to figure out how to get those other carbons connected. And that's where the proton NMR is going to be especially useful. So what do I see here? Well, I also can confirm these aromatic rings here. Well, I shouldn't use a resonance arrow. The aromatic structures, because I've got proton peaks between 6 and 9, right? So that's the range where my hydrogens are bonded to aromatic rings. And multiplet indicating probably multiple hydrogens on the rings, adding up to a total of 6 hydrogens. So if this weren't substituted, it could hold 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So that probably implies that this thing, this fused aromatic system of 2 benzene rings fused together, probably has 2 things substituted on it. I don't know where, but if there was nothing substituted on it, there would be 8 total hydrogens of aromatic type hydrogens. And that would create an integration of 8. So if I have an integration of 6, meaning there are only 6 hydrogens of that type, I've got to consider taking 2 off. I don't know which 2, but I've got to take them off and replace them with something else. So now I've got the ability to count for 6 protons on aromatic, of aromatic proton type. All right, so let's take a look at the other things the Proton Nmr is telling me. So here I have a signal around 4 ppm. It's a singlet, it integrates to 3. Typically an integration of 3 implies a methyl group. I've got 3 equivalent hydrogens. And here, typically a methyl group would only appear around 1 ppm, right? Just like the methyl group we saw over here. Hydrogen A. Oh, this wasn't A, it was G. Hydrogen G. It's around 1 ppm. So in this structure here, if this methyl group is around 4, it's got to be bonded to something very electronegative that's pulling the electrons away, de-shielding those hydrogens, shifting them down to around 3 to 4 instead of where they would normally appear around 1. And that's a pretty big difference between where they would normally appear around 1 and where they're appearing around 4. That means X is probably quite electronegative, like an oxygen or a fluorine or something like that. Can't be a fluorine though, right? Because if it were a fluorine, that would complete the structure. There would be no way to bond anything else to it. Obviously, it's connected to this if it's all part of the same NMR, so that can't be. So probably it seems like an oxygen is the most likely thing that this carbon's bonded to. So that would account for these 3 protons. And then what I have here is a septet and a doublet with an integration of 1 to 6. So how do I get 6 equivalent protons? Right, so I have 6 here, and these protons are not equivalent, but that's why they're giving a multiplet, because they're all probably splitting one another and causing overlapping peaks roughly in this area. But this one here is suggesting 6 equivalent protons. They're all giving the same signal in the exact same spot with the same splitting pattern. So that means those 6 protons are probably equivalent. So how do I get 6 equivalent protons? That's usually occurring when I have 2 methyl groups on the same carbon. As long as all 6 of these hydrogens are equivalent, because they're all on the carbons that are on the same carbon, and as long as there's the ability for this bond here, whatever it is, to rotate, so those 2 methyl groups occupy on average the same environment, then all 6 of those protons would be equivalent. And in order for them to produce a doublet, there has to be 1 hydrogen on this neighboring carbon to split these 3 into a doublet, split those 3 into a doublet, and those 2 doublets would be in the exact same spot, so they would really just give 1 doublet with an integration of 6. And then that would also account for this proton here, one proton, that's a septet. That would be this one proton. And it would be a septet because there are 1, 2, 3, 4, 5, 6 neighboring protons. And by the n+1 rule, that would give 7, which is septet. Right? So that hydrogen would be a septet as long as it's not being split by anything on the other side. So now I have the pieces to put this puzzle together. I've got this group. I've got this group. And I've got this group. Those are my puzzle pieces. I've got 2 carbons that need groups attached, and I've got 2 groups with which to attach those carbons. So I can just connect them however I want. In this particular case, there's no way to know from this exact NMR data I gave you what the exact structure is. We don't know whether these 2 groups are bonded at this site and this site, or whether they're bonded at, because they're not equivalent groups, they could be really bonded anywhere, and that's going to create the asymmetry that means that none of the carbons on the ring are equivalent, and that will give us the 10 unique signals for all 10 aromatic carbons. So I don't know which 2 sites these 2 groups are going to be bonded to, but at least for my structure to be consistent with the data and not contradict with it, it doesn't really matter. So I can put one of those groups wherever I want. That's this group here, and the other group pretty much wherever I want. And then the other 1, 2, 3, 4, 5, 6 hydrogens would account for the integration of 6 for the aromatic hydrogens. So that structure, or really any structure with 2 aromatic rings fused, a methoxy group, and a isopropyl group, would be consistent with that data. As long as I put the methoxy and isopropyl group on any 2 of these carbons, obviously, except not these 2 because they already have 4 bonds. Any questions about any of that? Well, that is all that I prepared to discuss, so that's a pretty decent hour and 20 minutes of review. Does anyone have any other questions? Yeah, I'm recording this, Ethan, so if you missed any part of it or you want to review it over at your own pace, you're welcome to do that. I'll be posting the recording here on both my YouTube page and the Canvas course page as soon as it's uploaded and processed after I finish recording. Cool. Any other questions? Well, I'm gonna